First of all, I wish you the many new results in all kinds of your activities, including this high-level mathematics you are doing. And thank you for the invitation. So the aim of this talk, in fact, is to present a powerful method, both for solving the direct and inverse Sturm-Liouville problems on finite and infinite intervals. In fact, the tools are very simple, but the results are surprising. So first of all, what kind of transmutation operators, or sometimes they are called transformation operators, I'm considering. The first one is the transmutation operator, which corresponds to the Sturm-Liouville operator, Sturm-Liouville equation on a finite symmetric interval. Here, in general, Q can be complex valued. Rho in this talk will be always the square root of lambda, such that the imaginary part of rho will be greater or equal than 1. So if we are looking for a solution of this equation satisfying these initial conditions, then when Q is from L2, let's say, on this interval, it's a very well-known fact, classical fact, that there exists a continuous function K such that this solution U is just the image of the action of a transmutation or transformation operator acting on the exponential function. So this operator appeared first in the work of Povzner in 48, and then in hundreds or if not thousands of publications, including, for example, such important books as the book of Marchenko and Levitan. The main feature of this operator is that the kernel of the operator doesn't depend on the spectral parameter. This is the most important thing here. And in fact, up to now, only the existence of the transmutation operator in such a form was really used, and some its basic properties. But for practical usage, only very few attempts existed up to now. The second operator, transmutation operator, is the operator with the boundary condition in the origin. So if we are looking for a solution of the same equation, but already on this interval from 0 to b with such initial conditions, so phi is equal to 1 in the origin and its derivative is equal to some complex constant h small, then it is just the image of the cosine under the action of the transmutation operator, which also is a Volterra second kind operator with a nice continuous kernel G, which is closely related to the previous kernel K. And the third one is the transmutation operator with the boundary condition at infinity. So all of them, of course, are very useful in all kinds of inverse problems. So if we consider the Sturm-Liouville equation on a half line, with Q being a real valued, here, well, for me, it's not that important, but sometimes for some results in this talk, it is important. So let us suppose that Q is real valued and satisfies this integrability condition. So it means that more or less Q decays sufficiently fast at infinity. This is the usual condition in scattering theory. So equation 1 under this condition possesses the unique so-called Jost solution, which I will denote by this E of rho of x. Okay? Rho is still the square root of lambda. So the Jost solution satisfies these asymptotics at infinity. It's very well known. So this solution E admits the following, sometimes called Levin representation. This is the same Levin of entire function theory, the classic of complex analysis. So he obtained this representation in 56, and of course it is considered also in different books by Levitan, for example, by Chardin-Sabatier. Precisely in this book, Chardin-Sabatier called this representation Levin representation. So here the kernel A is an L2 function. So for us it is quite sufficient. I will show you how I will use this fact. So these are three transmutation operators, which in fact what we do next, we just construct them and use them. So first of all, the kernel K admits this representation, this Fourier Laguerre series representation. Sorry. It just follows from the fact that K is in the appropriate space L2. Now, Pn here is the Legendre polynomial of order n, and so what can be shown is just that the series converges with respect to T in the L2 norm. If Q is continuous, then the series converges uniformly. The coefficients beta n are constructed by a simple recurrent integration procedure, which I omit here because it's simple, but it requires some more notations. So just believe me that it's simple and they are easily calculable, numerically, of course. So this was done in our paper with my colleagues, Navarro from Venezuela and Sergei Torbo from Mexico. Now, let us take this Fourier Legendre representation of the kernel K and put it into the transmutation operator. So just substitute it here. So we obtain this series where these integrals are easily calculable. So this is the result of this integration. We obtain the spherical Bessel functions here. So what is it? Is such kind of series are known in mathematical analysis since 19th century. They are called Neumann series in Bessel functions. Neumann, not John von Neumann, but Carl Gottfried Neumann. Well, why it is interesting, this kind of representation of the solution U? It's interesting because of the following fact. Sorry. So let us consider the truncated series, okay, up to a certain n. Then what can be obtained is an estimate, just this kind of estimate for the accuracy of the approximation by a truncated series, which is independent of rho. This result is easily obtained using Cauchy-Bunyakovsky inequality. And this is for rho being real. Rho is a spectral parameter, okay? So the estimate doesn't depend on the spectral parameter when rho is real. If rho is complex, then in the estimate we obtain the width of this strip where the complex already rho lives, okay? But essentially this is the same. So more detailed estimates, depending already on the regularity of Q, can be found in the same paper. Now, I will show you how it looks like numerically, so how it works. So what we do now is consider just one Sturm-Liouville problem on a finite interval, okay? So we calculate some of these coefficients. As I told you, this is just recurrent integration procedure, which is very simple, and solve this Sturm-Liouville problem with the aid of this representation. So this is the test problem, for example, for which the exact eigenvalues are known. So this graph, this blue one, is the absolute error of the first 100 eigenvalues. First 100 eigenvalues. You can see that it's at the level of 10 to minus 11. Just 20, in fact, it's 30 terms in the representation, in fact, because I started with 0. Okay? So the red curve is the relative error. So it is at the level of machine precision. So you cannot do anything better, in fact, if you work in the machine precision. So the relative error of the first 100 eigenvalues obtained in a fraction of second, in a fraction of 1 second. Now, this is the same, but for the next 400 eigenvalues of the same Sturm-Liouville problem, again, in a fraction of a second. This is the absolute error. You can see that it's absolutely uniform. Okay? And the relative error of the, so first 500 eigenvalues. These graphs can be continued up to 10,000 eigenvalues without any problem. No other existing method or algorithm is able to do more or less the same. So now, how can we use this representation for the inverse problems, for solving the inverse problems? So first, I'm considering the inverse problem on a finite interval. So it consists basically, without too much details, it consists of the following. Given two sequences of real numbers, lambda n and alpha n, satisfying certain conditions which I omit here because they can be seen in the book by Levitan and in many other texts. So find Q and the numbers h small and h capital such that lambda n should be the spectrum of this Sturm-Liouville problem. Alpha n should be the corresponding weight numbers of the same problem. Okay? This is yes, normalizing constants. Sometimes they are called weight numbers or normalizing constants in the literature. So this is the classical setting of the inverse Sturm-Liouville problems. So how we use our representation? First of all, I would like to mention that there are quite a few numerical methods developed for solving such problems. I mentioned here only some of the known works, but what is important here is that practically all more or less efficient methods are iterative. So you should guess more or less to make the first guess, the second, and so on and so on. And successively approximate Q, H small, and H capital. The method which I show to you now is just a direct method. You reduce the whole problem to a system of linear algebraic equations. This is in few steps. So first of all, we take this representation of the kernel G. What are the coefficients an? In fact, here, now it doesn't matter. The only thing which matters is what is the very first coefficient, a0, a0, okay? It is precisely, it's just easily can be shown that it is precisely that solution of the Cauchy problem, phi, okay? Corresponding to rho equal to 0, okay, minus 1. So this is what matters. What are the next ones? I don't care, okay? So I just know that this representation exists and so on. Now, due to this information from here, we just can recover the potential Q from this very first coefficient A naught. So this Q can be recovered in this way. Having A naught, I recover Q. H is obtained as just the derivative of A naught in 0. And finally, the number H capital can be found using this. Okay. So now, how we use all this? First of all, we remind that there exists such a nice equation like the Gelfand-Levitan equation. It's a fantastic thing from the spectral theory. So the equation tells us the following, that the kernel G is related with this, with this function f, which is constructed having this spectral data, okay? Having spectral data, it is constructed in this way, and G is related with f through this Gelfand-Levitan equation. Okay? This is also very well known. So what we do, we just put our representation for G in this equation and see what happens. So we put it here, just integrating. So like before, we obtain some series of Bessel functions. In fact, to prove the convergence, at least in L2 sense, it's very easy. It's a little bit more difficult to prove some, for example, here uniform convergence and so on. But the L2 convergence is sufficient for our purposes here. So now I multiply this equation by the Legendre polynomial, okay, just to make use of the orthogonality of them. What we obtain is the linear algebraic system of equations for the coefficients A, M, okay, with these coefficients here, with these entries of the matrix of the system and with this right-hand side of the system. So next step, we just truncate this series, okay? Just truncate them, because we have some only finite number of spectral data. So this rho n and alpha n. So we truncate them and solve the system to find our A naught, A0, the very first coefficient. So I am considering this truncated system, okay, and solve it. So this is the whole algorithm, in fact. Compute these truncated guys from the system. Then for a set of points, solve the system, obtain A naught, and then compute Q. So this is the whole procedure. It is published in this paper, Journal of Inverse and Ill-Posed Problems. Now, for example, let us consider this potential Q, okay, from this paper, just to show you how it works numerically. This is the potential, and with the red circles, this is the recovered potential. In this case, n, the number of equations in this system was just 6. It was sufficient to recover this potential. Now, half line. So here it's even more interesting, in fact, because I can say that in a sense we trivialized the problem on a half line. So I will try to explain it now. So let us consider this equation on a half line. Q is real valued, short range potential, so it means that it satisfies the same integrability condition. The Jost solution has this form, we already saw it. Now, we use the fact that the kernel of the transmutation representation from the Levin representation is just in L2. it implies that this function A, we just changed the notation slightly, this function A will be in L2 with this weight, okay? Then this function A admits just the series representation in Laguerre polynomials, okay, the usual thing. So we use this Laguerre Fourier Laguerre expansion of A to obtain this representation for the kernel A capital. Now, the question, of course, is what about these coefficients? Okay, so the representation exists; it converges in the L2 sense at least. But what about these coefficients? I will answer this question a little bit later. But first, I'm just using this representation. I take it and put into the transmutation operator, into the Levin representation. So I put it here, okay? These integrals are very easy. They are from the table. So I obtain this representation for the Jost solution, okay? With some coefficients an. The only point up to now is that they exist, nothing else, okay? But let us see more closely to this. So here it's very natural now to introduce this change of variable, okay? So let us denote as z this guy, this quotient, okay? So this, of course, is just a Möbius transformation of the upper half plane where my rho lives, okay, onto the unit disk in terms of z. So the Jost solution in terms of z admits the following representation, okay? And now I substitute this representation into the Sturm-Liouville equation. So what we obtain is a simple, in fact, simple recurrent integration procedure for calculating the coefficients an, starting with the first one, a naught here, a0, which is just the Jost solution corresponding to the precise value of the spectral parameter rho I over 2, okay? So I just need to compute only one Jost solution, okay? And all other coefficients then, and all what follows, just follows from this computation. Only just one solution, Jost solution, for this value of rho, and that's it. So it is from our very, very recent work with my colleagues, Briseida Delgado and Kira Khmelnitskaya. Now, what can be found also quite easily, that it's necessary that these coefficients tend to 0 when x tends to infinity. So, first of all, the estimate. If we compute these coefficients, then the following estimate is very easily obtained. Once again, look, for example, when the imaginary part of rho is greater than 0, then we have this uniform estimate where it becomes better when the imaginary part of rho is greater, okay? And in the case when rho is real, this is the exact equality, but in the L2 norm. It's just the consequence of the Parseval equality, nothing else. Now, okay, I will omit here this part because, in fact, we need not only the Jost solution, but also its derivative for all computations. So we do the same for the derivative. We obtain the representation, more or less of the same kind, with the coefficients dn, okay, and this representation for which also a very simple procedure to compute them is available. Now, what is the forward spectral or direct spectral problem here for the half line? So we are looking for the solutions of this equation satisfying this initial condition, okay, with some h real now. And the spectral data in this case consists of probably, if exist, the yes, discrete part of the spectrum, which are just negative, if exist, negative eigenvalues with corresponding weight numbers. And the most difficult part in computations is precisely to compute the spectral density function for the continuous part of the spectrum, because there are some works, quite many works where people compute the discrete spectrum in this case, but it's relatively simple numerically. And only about 2-3 papers, in fact, where there is an attempt to compute the spectral density function. Okay, so I will mention it later. So how all these spectral data look like in terms of the Jost solution? First of all, the eigenvalues are zeros of this quantity. Okay. Now the weight numbers alpha k can be computed in this way, where delta 1 is the derivative with respect to lambda of the same quantity, okay? Which is quite difficult to compute, in fact, in practice, the derivative with respect to lambda. And finally, the most important, this function v lambda, which is just the derivative of the spectral density function, because the spectral density function itself doesn't matter, nobody needs it. What is needed is its derivative, okay? Because in all the spectral expansions, what appears is the Stiltius, okay, with d sigma. So the thing which is needed is precisely this v, which is the derivative of sigma. So this v can be computed in this way. Okay? So all this, for example, can be consulted in this book by Yurko. Now, okay, I mentioned here just the publications where some attempts about the computation of this spectral density function are made, and in fact the difficulties are clearly seen here. So the problem of computation of the eigenvalues in our notations in terms of this parameter z reduces to finding zeros of this function delta rho, which in terms of z has such a form. And z, in this case, belongs to this interval from -1 to 1. Okay? In terms of z, it's just that. So z equal to -1 corresponds to lambda equal to -infinity. And the z equals 1 corresponds to lambda equal to 0. Now, for this quantity, we also have such a representation. And schematically, in terms of z, where is the spectrum of the problem on the half line? Look, here is the discrete spectrum just on this interval from -1 to 1. And here is the continuous spectrum. Okay? So what we should do is to do just two simple calculations on two finite intervals, nothing else. So how it looks like numerically. Okay, first, the part of the continuous spectrum is computed in this way, where this phi is the same from the previous slide. Okay, numerically, the result, for example, so let us take this potential, Q satisfies all what we need. In this case, delta has this exact form, so we can compare our results against the exact values. And so, for example, if the constant h is equal to -1, in this case, there exists one eigenvalue, which is approximately this number. So we compute first this Jost solution for this value of the parameter rho by using the method from our paper of 2010. We obtain it with the accuracy of order 10 to minus 14 and use it for all computations. And so the approximation of this of the eigenvalue is immediate. So just n equal to 9 terms, we have the accuracy of 10 to minus 13. This is the maximum absolute error of the function v of lambda. Okay, so it also converges very fast. And here is how this function v, which is the derivative of the spectral density function, looks like. So how it is obtained. The inverse scattering problem on the line can be solved using this representation. So I just, okay, more or less like in the first part for the finite interval, this is the same procedure. We just take this representation, put it into the Gelfand-Levitan-Marchenko, in this case, equation, and obtain a system of linear algebraic equations. So I omit here this detail, just one example. Here is the potential Q. So with the corresponding scattering data, and here is the numerical solution. All this works in fractions of seconds. So the recovered potential, okay, in this case, just m equal to 10 means that only 10 terms of the representation. The absolute error here is already of the order 10 to minus 2. Slightly more terms, the order of error is 10 to minus 5. So more or less, this is how it works. Thank you very much.
Thank you. Thank you very much for a very interesting talk. Remarks or questions? Please.
You use Laguerre polynomials for expanding some respective kernels, right?
Yes.
And because you consider a Sturm-Liouville problem on the half line.
Yes.
This is reason.
Yes.
But if you, for example, consider on interval or real line, so you can use other classical polynomials, Jacobi or Chebyshev and so on.
Yes, thank you. On the finite interval, the first problem which I showed to you, they were the Legendre polynomials, precisely for the finite interval. On the half-line Laguerre polynomials. But in fact, you are right, you can use any orthogonal polynomials. Probably it will not work the same, okay? Probably the efficiency will not be the same in this case. No, up to now, no. What we have is... Yeah. I'm sure. What we have is, for example, the same as for the finite interval, but for perturbed Bessel equation. So Bessel operator plus Q, plus the potential Q. And in this case, also the Jacobi polynomials should be used, precisely depending on the parameter in the Bessel. So you have in the Bessel equation alpha by alpha plus 1 over x squared. So depending on this alpha, you choose the polynomials. But in fact, you can use any orthogonal system of polynomials.
It's probably, I need to tell, thank you very much to all participants, and thank you very much to organizers and to our men.
I'll try to say something, if possible. First of all, I want to thank all the speakers for their excellent talks and beautiful gifts they gave to me. You know, that I hope you like this conference, but this is this is mainly to the efforts of my former students, Alexander Kamlov and Roman Palverev, who really sacrificed themselves in order to make this conference successful. I should also thank the people who also helped me a lot: Sergei Suetin, Stefan Nemirovsky, Sergei Sergeyev. And of course, I am grateful to the all colleagues from the complex analysis department, which is headed by Evgeny Chirka. All, in some respect, they helped me. And the last but not least, I should thank the sponsors, as it's usual now. So the sponsors were, first of all, Steklov Institute, who gave us this hall, and then Higher School of Economics, where many of you lived, and I think the conditions were quite good. And also Russian Foundation for Basic Research. They gave us some money, which we pay for your stay here. Thank you all.